Okay, let's write a program to calculate the falling. I've started up Anaconda Navigator and I'm going to launch a Python notebook. It comes up a list of files. I'm going to decide which directory I want to put it in. So let's say I put it on the desktop. And then I'm going to create a new Python 3 file. Give it a name, something like base jump. Okay, so let's start off. Let's define some variables. Now I put a slash in front of something. That means it's a comment, which means it has no effect on the computer. The computer ignores it. It comes out in a different color to show that. But it's a comment for humans to read. It's very important when you write computer code to document your code, write comments to make it more human readable, because far more time is spent debugging code, finding things that are wrong with it, modifying it, changing it for another purpose, than is ever spent writing it in the first place. These comments help you, if you come back 6 months from now to this piece of computer code, understand what all the things were doing, which will save you a lot of time in the long run. So bear with me. It may take a bit longer right now, but write comments. So what do we need? We'll need the density of air, because we're going to use drag. We'll need the gravity, 9.8. How heavy is the person dropping? Let's give them a mass of, let's say, 80 kilograms. And cross-sectional area for someone with a wingsuit might be about 2 square meters. And drag coefficient of, I don't know, about 0.7, let's say. Okay, so I hit Shift-Enter to run that, so it now knows all these things. We can check. If we just type rho here, Shift-Enter, it'll tell us what the value of rho is. We've defined the constants, so now we're going to pick our starting conditions. The equations we've worked out tell you how to update the position and velocity, but they don't tell you where to start. You have to choose that. Where you start, your position and velocity will depend on the situation. In this case, let's start on top of a 300 meter, not 3,000 meter, 300 meter high building, and we'll start with a downward velocity of 0. And we need to pick a starting time, and let's start with a time of 0 as well. Okay, Shift-Enter on that. Now we need to set up our loop. We're going to need to pick the time step. We'll call that dt, and let's pick 0.1 seconds. Remember that the time scale for things to change was about 2 seconds, so we want a time step that's much less than that. Be careful about this. If you were doing some other situation like orbiting stars, a time step of 0.1 second would be ridiculously short. It would take forever to calculate anything. On the other hand, if you're trying to look at the acceleration of an electron in an electron gun, then the time step might be milliseconds or nanoseconds. So it's always important to work out how fast are things changing and to set your time step appropriately. One of the most common bugs we've seen is choosing an inappropriate time step. You can always tweak it later, but it's good to start off with something that's at least roughly right. Okay, and now we need a loop. So we're going to use a while loop. While means everything inside the loop is done repeatedly until the condition is no longer met. So what's our condition? We might pick while h is greater than 0. So this is while you're still in the air, with a colon at the end. Now, let's start off by printing where we're up to. It's not printing, it's print. And let's print the time and the height and the velocity. Okay, now let's work out the force. So force, we have to pick which direction we want to measure everything in. I'm going to count everything positive upwards. Height increases as you go upwards. So if the force is upwards, it will be positive, downwards negative. If acceleration is upwards, it's positive, and so on. You can pick whichever direction you like, but you just have to be self-consistent. If you pick a different direction, you might have to add plus or minus signs. This is the second most common mistake after picking the wrong time step. Being not careful enough about the signs of everything. So we're going to have gravity. We're defining everything as positive upwards. Gravity is downwards, so it's going to be minus m times g. And then we're going to have the drag force. Now this is going to point upwards because the object is falling. So go half times c times a times the density times v squared. Remember, v star star 2 means squared. Okay, that's given us the force. We can therefore work out the acceleration, which is just force divided by mass. You could put this all into one equation, but often it's good in a computer programming language to split it over several equations just to make it simpler for the human to read. The computer doesn't care if it's 1 or 2 or 3, but this way each equation is pretty simple and human readable, which will help you when you have to debug the code in the future. And now we need to do the updates. We're going to update our time, and we're going to use the plus equals command. Plus equals means take what the value was before and add this new thing to it. So we have t plus equals dt, which means add dt to t. And the height is going to be, I'm going to have plus equals velocity times dt. That's just the Euler's method. And the velocity plus equals acceleration times the time step. And that should do it. Fingers crossed, let's try running it. Shift and return on this. Woohoo! And we're off. So what we have is the time starting at 0, and the height starts at 300 and the velocity at 0. Because the print command is at the top here, it prints the values before they've made all the changes. You could put it at the bottom, but what it's like at the bottom is just what you get it when you come back to the loop next time. So after one time step, the time has gone up to 0.1. The height hasn't changed because the height was saying plus equals the velocity times dt, and that velocity is a starting velocity, which is 0. So it's not moved in height from the first time step, but it has changed its velocity. It's acquired a velocity of about -1 meter per second, which sounds about right. In 1/10 of a second it should be accelerated by 1/10 of g. And now as you get to the second time step, it's starting to move down, and the speed is getting more negative, and so on and so forth. It's dropping. Notice that the numbers here, instead of being 0.8, it's 0.799999999. That's because computers don't ever hold exact representations of decimal numbers, floating point numbers. There's always going to be a small rounding error. It's small enough you can generally ignore it. In this case, it's very, very small. But sometimes don't get confused by the fact it's printing out lots of 0.9s rather than 0.8. So what you'll see is after a second, here's 0.99, it's got down to slightly less than minus 9.8 meters per second squared, which is what you'd expect from the acceleration. It's a bit less than that because drag is starting to kick in. And as you go down further, you see to begin with the speed's changing pretty fast, but after a while the speed's changing quite slowly. It takes a long time to get from minus 21 to minus 22 meters per second. It's continuing to drop, and down it goes. And now you can see the speed is really stabilized. It's sitting at about minus 29 point a bit meters per second. That must be the terminal velocity here. So at this point it's now falling at a fairly steady rate. It's slowly edged up in speed to minus 30 meters per second. It's very slowly edging up. And it keeps dropping until the last recorded measurement is when you're only 3 meters above the ground, travelling at 30 meters per second, 100 kilometers an hour downwards. Definitely a bit late to release your parachute there. And presumably by the next time it came to a negative height, and so the while command was not met and it stopped. So there we have a numerical calculation. It's told us the height and speed in the situation.